I'll promise to work a bit on carbenes then this afternoon. I'd just like to close here with 2-3 things. Maybe this is an old cup of tea because Alan Goldman has been here and he maybe have shown you all this again or already previously, and then you just skip it. Maybe not. So some of the CH bond activation, then once the system was established, of course, a next feature is that you start looking, can we optimize it? Can we improve it? Can we lower this 200 degrees to a lower reaction temperature? Can we enhance the activity? Can we get higher productivity of the functionalized alkane? And so one thing that started was, of course, to functionalize the ligand and see what donor groups play a role. And here's my question to you. You know, we understand, well, you'd see here the activity. So what is the effect of the substituents and why is this the case? Can you rationalize this? You know, you look at the turnover numbers, you look at the turnover frequency, you look at the substituents, they're here as well. Do you see a trend? If you see a trend, what is it? Why is it? And we're here chemical, not physical. Huh? A trend is not a mathematical correlation that has no exception. Huh? Trends live from exceptions. But do you see a trend? Huh? So the more electron withdrawing, the faster. More electron withdrawing means we shift the equilibrium on this side rather than on this side. The more donating, the more we have oxidative addition. The more withdrawing, the more we have reductive elimination. And of course, elimination of dihydrogen from this compound is more difficult than elimination of dihydrogen from this compound. So the activation energy should be lower, the rate should be higher. Yeah? So we understand. Improvements, other improvements, so apart from having functional groups, included in particular to change a bit the geometry.
Methyl and methoxy are electron
donating.
Yeah, but still they are showing higher activity as compared to hydrogen.
Yeah, not really. Here's the hydrogen and here's the methyl, a bit lower, huh? A bit lower. The methyl. The methoxy, the rate a bit lower, but then the turnover numbers are higher. So I think what we have to be careful here is we have to look at the turnover frequencies really. They tell us something about the activation energy. The turnover numbers, and you'd see here how product inhibition plays a significant role. After 8 minutes you have almost full conversion. Well, no, you have 50% conversion. In the next 40 hours you have only the same activity as in the first 8 minutes. So clearly there's something happening that totally deactivates the system. But if you look at the frequency, I forgot what the asterisk here is. That may be the PCP. So that may be the PCB, so with carbons here. And then with the oxygens, here we have the oxygens. I should have noted this. So with the oxygen 1.9, with the proton 1.9, if we have a donating group, it gets slightly down. The fluoride, of course, the fluoride is an ambivalent donor group. It can be withdrawing and donating at the same time. And it's very hard to predict whether it's the pi or the sigma effect that prevails. So I would probably have the fluoride as a thing, as an outlier. But the slowest would be the methoxymethyl, faster is the hydrogen, even faster are the electron withdrawing perfluorobenzene or other fluoride containing aryl groups. So I would, if you look at just the turnover numbers, you get a slightly distorted image, but these turnover numbers of course tell us something about how robust the catalyst is and how susceptible to side reaction it is, and not necessarily about how active it is. So, can I go to the?
So that highlight insertion in the G, the product G. The highlight insertion
This one here.
Here, that one position or two position?
Here it doesn't. This can go both, and this. So this then enters the new isomerization cycle. So of course they're almost the same energy. You know, so from the hydrogenation cycle we get here. Now here, a secondary carbene ion is better stabilized than a primary. Yeah? Substituents help to stabilize charges. So that's why we get rather soon a mixture. So what you're asking, whether then in this guy here, this can go reversible.
That F is in F which position will be favored? That one position or two position?
This one?
From these places.
From this one?
From E to F.
E to F is 2 position. From E to F is 2 position. It's this one here that inserts. So you keep the so you protonate this position here. You protonate the end position, so this one gets metal bound.
No, generally, if there is alkyl chain, if we think about that electron is pushing and that hydride is migrating, so can I
How large is the difference of an R group compared to a proton? In terms of donor properties. What's the inductive effect of a methyl compared to a hydrogen?
not that much? So that will be electron pushing. So I can say electron is coming actually here. Like diving further than the electron inside the reactor, whatever mixed with that will get the slabs.
You're not happy? So if we have an electron withdrawing group, the polarity is this way. If we have an electron donating group, polarity is this way, no? In the olefin. But the difference is small. And sterics may be against you.
Actually, sir, whatever
You know,
I was thinking that probably the stability of the product is one of the key things here. Because thermodynamical inner side double bond is more stable than the terminal double bond.
yeah,
That's why this is product.
yes. And that's why you get even all the isomers. Yeah? Okay? So if here the other one is inserting, you get even the more inner propagation. But there's very little bias, so you get a statistical mixture at the end. But here you see some effect in changing the geometry. So if you use a five-membered central ring, this has geometrical effects. So I've shown you that this, I draw this perfectly 180 degrees, but I said it's about 150, 160. If you make this a five-membered ring, that means that these substituents go even further out. So as a consequence, this P iridium P angle is even smaller, goes to 140, 135. And as a consequence, the space that is opened with dihydrogen release becomes even larger, so activity increases. So that's the feature of having these five-membered things. But for five-membered rings to be stable, you either have here an ingenious five-membered ring, or you have a ferrocene or a metallocene, and then you can modulate it. Good. And then people have coupled this, like in transfer hydrogenation, they have coupled it to very interesting cross second catalysis, because once you have an olefin, you can do olefin metathesis, so you can change it, and what you do, and then you can use this just as a hydrogen transfer catalyst. Basically, you dehydrogenate, you store the hydrogen on the iridium, you rehydrogenate. So what you do in one pot is a alkane metathesis, where you change a small alkane to a large one. And now we're talking again to what we said about valorization of alkanes, because now you can think of having gases, butane, propane, and make out of propane hexane or pentane. Now suddenly you get into dimensions where you make out of a gas a liquid, and that could be interesting. What's more is that you can use gases that are used maybe as natural gases. You can make out of this petrol, C8 compounds. Or you can make out of pentane hexane, you can make kerosene, C10 compounds. Or you can make out of these even C12, C14 carbenes, diesel. So suddenly you have a process to store energy in a much more common way, and you have access to new resources for petrol, diesel, kerosene, whatever we need to power our engines. So that's a bit what I wanted to tell you about the CH functionalization, and then I promised you we will do a bit more on ligand design, including synthesis and properties, catalytic applications, or off the norm. The basics you know. Okay? Catalytic applications? You know? Third and fourth. You're all happy with that? Do we have to vote? Say?
Let's have some basics.
Basics.
Some basics.
Okay, a few basics. What we do, we have 100 minutes. So we do 15 minutes basics. Yeah? Okay. So you all know carbenes, two states, singlet and triplet. Singlet having two degenerate orbitals. Singlets, two non-degenerate orbitals. So there's a gap that spans between the sigma and the pi orbital. The pi orbital has to be filled by external systems. The sigma orbital can be used for bonding. Bending helps to stabilize the singlet carbene. So that's one of the things when we talk about heterocyclic carbenes, we introduce the bending from the very start. That's why we have almost very little singlet character in all our heterocyclic carbenes. So I save you this, you can all read in chemical reviews. So what's the orbital situation? The only thing I should point out is that typically the pi orbital that is then part of the bonding is not so available. So pi acceptor, pi donor properties of carbenes are due to that orbital situation fairly minor components. Sigma donation is by far the most important donation interaction with carbenes. You need heteroatoms somewhere either close or remote to make the carbene reasonably stable, but once you have a metal to stabilize it, you can as well have carbon-only carbenes, like 7-membered cycles. Okay, how did it start? There were two lines of carbene communities. In one case, more the physical chemistry side, they started to generate carbenes in matrices. So where the molecule is isolated in a matrix, then they reacted mostly photochemically and generate the carbene at very low temperature. They can freeze it and they could study it. This has gained access to some of the fundamental properties of carbenes, but it was not useful because once they're in the matrix, they're isolated and you can't add anything. And Guy Bertrand was probably one of the first that started to look at the carbene in condensed matter, so in bulk properties. And he was the first one to isolate and actually characterize a free carbene, which was this one here, 1988. It's worth to go and have a look at this paper, because if you read that paper, it is impossible to read the title. It's like a 3-line chemical compound name that he says he produced in 1988. And only a year later, he had another JAX paper where he looked at the properties of this compound, and only there, you see the appearance of the name carbene. So in his first paper, he thought this is an ylide, and he only classified it as an ylide. And only in discussing with colleagues and peers, he realized that what he had was a carbene and not an ylide. So, even bright discoveries, they take their while. So a year later, he called it a carbene, and yes, of course, it was a carbene. Of course, we all know it's also a ylide, and the transition is fluent, but there's a different connotation if you can look at carbenic properties. Then, at about the same time, Arduengo started to work. He was at that time in DuPont, or in Dow, I don't know anymore, but nowadays they're anyhow the same, doing research in polymerization catalysis. And he looked at an organic radical initiator and wanted to develop something that could initiate polymerizations. So he developed a carbene as an initiator. He went to the glove box, he synthesized that thing, and then it took him a while, and they started to test it. And when he went to the company, to the production site, he saw there was like a bag of, like sugar. A bag of white powder was there sitting out somewhere on the floor. And he asked, oh, for God's sake, what is this? And the guys, the technicians told him, oh, but that's your carbene, sir. So that's how he discovered that his carbene is totally air stable and can be bottled. So you see as well, those guys needed a bit of help and a bit of courageous co-workers that helped them make the case. But so that's two anecdotes of how the carbenes have been discovered, and the rest many of you know. So then he managed to crystallize it. He published the first crystal structure. So here's the first free carbene that was isolated. Here's the first free carbene that has been crystallized and structurally characterized. And then it didn't, well, it took a while because this guy here is sterically so encumbered, you could not do anything but study the carbene. This guy here was much different, because now suddenly this pi electrons, or this sigma, this sp2 hybridized orbital is fairly exposed. And while Arduengo couldn't do much with it, other people picked it up and started to do chemistry. And of course, this was also a bit influenced by people that have started to work with carbenes like 20 years back. Like in the early 70s, late 60s, Oefele and Wanzlik and Lappert made carbene complexes. So they used this syntone and put the metal there. But they used totally different routes that were not so amenable. But it worked. They made the complexes, and then having suddenly access to the free carbene totally flattened the road for many, many people to travel. So what do we know? We know, carbenes have then probably been analyzed to death. Various parameters have been looked at. What we know is that principally the carbon-carbon bond in the unsaturated carbenes has largely double bond character. So it's quite olefinic. You can do epoxidations, you can do oxidations as you can do with other olefins. So it seems that this double bond is more double bond character. You also see this when you look at structural properties. This bond is relatively short. While there's a delocalization in the NCN unit, and you'd see that typically these bonds are all the same, and the angle is very narrow, and that stabilizes the sigma complex. People have looked at carbene NMR, at the carbene NMR chemical shift. There seems to be a little trend in benzimidazolidines to imidazolidines to saturated imidazoline ylidines. But it's these three classes that play a role. But then we have to be very careful. As soon as we add a metal, we cannot use the carbene as a diagnostic feature, whether it's a carbene or not, because the carbon NMR shifts are perturbed by the metal, by the nitrogen, by paramagnetic components. So we cannot use carbon NMR chemical shifts as we can use proton NMR shifts, where in proton NMR the paramagnetic components are totally irrelevant. So we have different resonance structures. We have to, and you see a bit everything. Yesterday I talked about this dichotomy of having more mesionic structures and more carbenic structures. I think we see that in the free carbene there is some relevance of the free carbene. In the complex we have much less carbenic character and more single bond character. Here you see two of those classic chemistries that have been done with carbenes that are very similar to olefin chemistry. So it seems that this double bond is rather insulated from this NCN unit. And you can do deuteration, you can do chlorinations, and Denk has as well done oxidations. There's a bit of a problem in nomenclature with carbenes, because carbenes, we call them all N-heterocyclic carbenes. We have also these classic Fischer and Schrock carbenes. And if we look at the compounds, we realize that the carbenic character is, especially in the Fischer carbenes and the N-heterocyclic carbenes, relatively low. So if you look at the representation of our carbenes, we usually use such type of a representation with a metal carbon single bond. Fischer always uses a metal carbon double bond. So are these more carbenes than these? Not at all. They're exactly the same. They have the same bonding principle. We have here electron withdrawing substituents. That's what we have with Fischer carbenes as well. So the orbital situation, the stabilization of the carbene is the same. And the properties are the same. Look at this Fischer carbene here, this chromium system that looks like DMF, just having, instead of an oxygen, a chromium substituent. And it does the same. This methyl group and this methyl group are inequivalent, like DMF at low temperature. So what's the conclusion? At room temperature, this resonance structure is not so important. This resonance structure would have free rotation around the nitrogen carbon bond. What is much more important is this resonance structure, which has no free rotation between the nitrogen and the carbon bond. And this resonance structure is, of course, extremely similar to what we use for the N-heterocyclic carbenes. So what's the problem? The problem is history. Fischer, in the 70s, 80s, he used this notion. This has been used for everybody. And still, the Fischer carbene community would draw all their molecules this way. The N-heterocyclic carbene community, if you look at very early papers, you see the double bond notion. And then spectroscopy, crystallography showed that there's almost zero double bond character. So everybody switched to this thing. So carbene chemistry looked at the bonding at the stage where history could be rewritten. Fischer carbene chemistry was at that stage 30 years old. It could not be rewritten. So you cannot teach those folks other things, but de facto there's a huge discrepancy in how we draw the thing. It's exactly the same bonding interaction, it's exactly the same situation, so there's a huge overemphasis in the writing difference, which is not existent. Now, I know that some of you guys are drawing your carbenes a bit more this way. So that's my plea slide. I advocate to not draw it this way. I think, because here we miss 2 pi electrons. We have those pi electrons here in the double bond, or we have it in the NC bond, or in this NC bond. So formally we would need to draw a negative and a positive charge. I think we can avoid this as we do this with DMSO. In DMSO, formally we should as well write the sulfur plus and the oxygen minus. So we can just draw the neutral structure, but you recall that here we have the 2 electrons drawn. Or we draw the 2 electrons here, the 2 electrons from the lone pair, the 2 electrons here, and we get the 6, the aromatic structure. As I've shown you in previous slides, there is significant double bond character here, so that's why in many cases we prefer this representation. But we'll see as we go to abnormal carbenes, we lose that bonding description a bit. And so most often you see it as well this one. This one here has the problem that you find all these chemical structures also in cyclopentadienyl type chemistry or cyclopentyl type structures. So a magnesium, a Grignard compound would have that structure. This is clearly an sp3 carbene. And if you make a Fischer carbene, you would have this one. So where are we here? Is this an sp3 or an sp2 carbene? I ask you there to look broader in history. Now, the last 10 years, everybody who saw such a structure, without looking at the electrons, we knew, N-heterocyclic carbene. In 30 years' time, there may be developments that go in a different direction, and we go back to our original notion. This carbon has 3 bonds, so the fourth is a hydrogen. And I have papers seen, you know, where they stepwise methylated this compound. The first intermediate is this one. And then the proton is left, the electrons go back, and you have to get the free carbene. Now you have to think of this. We usually don't draw the proton. How can I distinguish this compound from that compound? So why is this a carbene? So that's my plea to not forget those 2 electrons. And I know maybe I should talk more to your supervisors than to you. I usually or sometimes do this in my referee comments. So whenever I have, not always. So, because otherwise you all know that I refereed your paper. So I don't do this always. I might do it next time I see a very brilliant paper, so you know who wrote it. Anyway. But so I think there's a merit in showing those 2 pi electrons and not to obscure them. Good. What's the donor properties? The donor well, I should probably skip this a bit. The properties have been measured with various factors. We know by now that the donor ability is very difficult to modulate via the backbone, but it's easier to modulate it via 2 nitrogens. And that fits in this notion that there's an olefinic pi interaction and NCN pi interaction. So we can change the carbenic donor properties much more via this network than via this network. And we see this as well, that the benzimidazoles are more similar to the saturated carbenes than to the unsaturated carbenes. So again, this indicates that here, you know, the double bonds are really in a different pi I skipped this. We can show that there is interaction between the metal and the metal, not with this notion, but if we go square planar. How do we synthesize? The synthesis I go over. I go quickly. So we have different methods to synthesize. Maybe the most classic one is this 4-component synthesis. Starting from glyoxyl, we do a Schiff-base condensation. We get the diimine. We ring close with formaldehyde, and the same can be done with phenyldiamines. Here you have the option to selectively introduce 2 different R groups. Then here we can put. Some of those functionalized imidazoles are commercial. We can either do an SN2 substitution or some type of Ullmann coupling with copper oxide and then an aryl bromide or aryl iodide. We can as well arylate. If we do arylations, we use harsher conditions, so we need a bit more stability in the R group that we have here. Then that's probably the most classic route to those imidazoles. Alkylations can be done with various sources. We can, at that stage, very easily modulate the X, the anion that is present in the imidazolium salt. That's very relevant then for methylations. When we methylate, we have like a number of routes. This one is probably the oldest one. That's the Lappert-Wanslick route, a diolefin, electron-rich olefin that can be cleaved with some metal centers. It's as well the hardest one. It's totally historical these days. Classic is a free carbene route. You start with a take a non-nucleophilic base, you form the free carbene, and then you can methylate. That route works with almost all systems that have relatively large or bulky R groups. It's tough to do it with small substituents like methyl ethyl because the free carbene is then not stable at all. So you have to be very quick, work at low temperature, but low temperature becomes an issue because low temperatures, the dimethyl imidazolium salt, for example, is extremely polar. So you cannot use all solvents. You need some polarity in the solvent because you have a lot of charge with little organic substituents. It also does not work if your substituent here is electron withdrawing. So you have a hard time, for example, to deprotonate imidazolium salts that have 2 sites. Why? Because these 2 protons become extremely acidic with the 2 electron withdrawing substituents. You can consider this imidazolium salt as a phenyl group, but stronger electron donating. So benzylic protons are acidic on their own. So this is a super benzylic proton there. So with a strong base, this proton goes. The same when we have electron withdrawing groups like carbenes. Very difficult. Imines, very difficult. And that limits a bit your ligand and complex scope. But luckily there are other methods. One is CH bond activation, which would be the cleanest, works only for a very few metals and for specific precursors. For example, we use nickelocene to methylate. Goes very clean, you form the CP hydrogen and you get the nickel carbene. Nice. Works with platinum 0, but then you do actually an oxidative addition. Did I write this somewhere? No. Anyway. Palladium acetate can work. And it works particularly if you have cyclomethylation. Then oxidative addition, dissociation reactions. So if this is a halide or if this is a silicon a directing group that you can easily cleave, this works very well. Also works very well if this is a carboxylate group. Then you do a decarboxylation, is a very clean reaction and a very reactive intermediate. We love this, especially for these small things. This is our favorite route for methyl substituents. That's a betaine, zwitterion. So this is a metal-induced process, we think. And you get the carbene by losing CO2. Very clean. Works in water. Easy. Very nice. Not that we use water regularly as a solvent, but we have a project where we look at metalloenzymes, and once you're working with enzymes, water is your name of the game. But so for decarboxylation, so this route is extremely clean for some of the metals, and especially the carboxylate is easily inserted if you have small groups. If you have bigger groups, you usually use a deprotonation, and then you quench with CO2. Now, if you deprotonate, you're already here. You better just add the metal precursor, then you make the carboxylate. Yeah, good. Then you can do transmetallation. So this is typically silver oxide that you use here, but you can as well use other precursors. Copper oxide has been used, and of course a variety of other metals can be inserted, and then you can do a transmetallation. Nickel, for example, has been used as well. So you can use nickelocene to use this route, then you have the nickel here, and you transmetallate with a platinum group metal. Cyclizations, very elegant, has been promoted especially by Eke Han. If you start from an isonitrile compound, this one here, you can start with, you can add a functionalized amine, you can ring close. This route has then propagated further by Stephen Hashmi as well to make abnormal carbenes, to make saturated carbenes, all types of systems. And works very well because the isonitriles, there's a few isonitriles that are available. It has a disadvantage in terms of you're not so free, or you assemble your spectator ligands at very early stage. Once you're here or here, it's more difficult to disassemble. And in many cases, you start with a di-isonitrile complex. So you make a dicarbene. You may like it, and it may be your choice, or it may be that the second carbene is actually a thing you don't. So, and then I already discussed this one. Oh yes, I forgot. So one of the other, in addition to the carboxylate route, there are these thermally protected, or these protected carbenes that can be used. Like alcohols or chloroform can be used to protect your carbene. You get something stable that looks like that, and if you heat this up, you go back to the carbene. So that could be as well an interesting method to kind of temporarily protect your carbene and then metallate it. So I don't go too much into the mechanism of how this metallations work. You see here the carboxylate that helps to thing. There's the carboxylate, decarboxylation, transmetallation. Maybe just one word for the transmetallation. We think that much of the transmetallation can be reversible, and the silver carbene that you form is in many cases super dynamic. So you have an equilibrium between the monocarbene X and the bis carbene cation species. And people have shown in the last 3-4 years that this is a dynamic equilibrium for many carbenes, not for all. So for the cyclic aminoalkyl carbenes, it seems that the silver carbene is stable. But for the N-heterocyclic carbenes, this is an equilibrium, and it depends on a million factors. The temperature, the concentration, the anion, you name it, it all plays a role. So as a consequence, any crystal structure you extract from this has to be taken with a grain of salt, or a salt of grain, whatever you want. Anyhow, so it's not the truth there. It's what solidified, what was the stable product under crystallization conditions. And here are just some of the crystal structures, and you go to that ChemRef and you'd see pages, but full and full and full of carbene silver structures. There's no pattern. There's no rule. And you see the silver anion look at this silver anion. Mamma mia. Silver X, silver X, silver X, silver X, you know, and we've seen silver 22, I23 anions. Anything assembles. Highly unpredictable. For many cases it doesn't matter, because we use the silver carbene anyhow for transmetallation, and the silver halide we filter off, so it's gone anyway. One important bit, in many cases, once we form the metal-carbon bond, we form this bond irreversibly. We have to add stimulation, specific reagents to make that bond possibly reversible. And that's a distinct difference to phosphine chemistry. Coordination compounds, there is a kinetic constant dissociation, reassociation. And if we have a chelate, the dissociation never gets far and you rebind, so the 99% of the cases we look at the compound, it's chelating, and we don't see then the dissociated system. But so that helps to equilibrate. And so this guy here is not favored, and we get the chelation in phosphines spontaneously. With carbenes, no. That kinetic lability of the metal-ligand bond is not there in carbene chemistry. When we start with such a ditopic ligand, under conditions, and under specific conditions, we either get a bimetallic species or a monometallic species. And we have either or. There's no equilibration. Once we have this, we can heat and boil and cook and what we want, it stays what it is. If we have this one, it stays. So there's no equilibration, and that has consequences in how we synthesize. So we have to be very careful in manipulating concentrations and stoichiometries if we want to have the bimetallic or if we want to have the chelating species. In some cases it is reversible, and for example Bob Grobs, he could show that that by using a carbene as a catalyst, he could actually make those trimetallic species, and he makes them by having the carbene bonding to the iron and releasing again from the iron. Very nice work, and we've ever since seen many examples where the carbene is only weakly bound. I'd say in many cases we talk here about first-row transition metals. And we understand this. Carbenes are very soft, first-row transition metals typically relatively hard, so the bonding interaction is much less. Iridium, ruthenium, rhodium, much more difficult. We've seen it with gold. I've talked about this yesterday. With gold, we see as well lability. Steric electronic parameters. We can measure the steric and electronic parameters by a variety of factors. One of the key factors, so sterically, probably the best description is the percentage of buried volume that we can measure, which describes which part of a sphere around the metal center is occupied by the carbene and its wingtip groups. I could not calculate this, but luckily our friend Luigi Cavallo has made a program. This program is freely available. You can access it from the web, and there's even a paper about it. You can put in your ligand structure, you click, it gives you the percentage buried volume. Very nice. You have all those slides. Whoever wants to have some of the references down here, Mandeep has them all. The other parameters that we can look at are Tolman electronic parameters and Lever electronic parameters. Tolman looks at the cone angle. Tolman looks at the carbonyl stretch vibrations, which have been designed originally for nickel tricarbonyl. And then you have the A3 stretch mode that looks at all those three carbonyls, and the stronger the ligand is donating, the more we have back bonding, so the more we have metal-carbon double bond, so the more we have, this is, forgive me, this is not square planar. Huh? They're all equivalent. This is tetrahedral. Don't know why I didn't change this. Anyway, so they're all the same, but so the carbonyl, the more we have, and here's some loop got. This is a very poor d orbital. My students wouldn't get a point for this. But the more we have donation, the more we have pi back bonding, and so we start to change lower the frequency the frequency of the CO stretch. So we can look at, and this has then extrapolated because the starting point for these nickel tricarbonyls is metallation with nickel tetracarbonyl. Nickel tetracarbonyl is toxic, not nice to work with. It's volatile, which makes it particularly unnice to work with. So that's not good. So people looked at rhodium and iridium surrogates and found correlations between the frequency drives of the rhodium carbonyls with the nickel and between the iridium and the nickel. There's a bit of a controversy because now we have basically, we lose the A3 mode, so here all the 3 carbonyls are symmetry related. Here of course the 2 carbonyls are not symmetry related. Some call it a cis and a trans carbonyl, which is a bit irritating because there's not something like a cis and a trans mode. Some call it an asymmetric and symmetric, but this implies that principally the 2 carbonyls are both in an A1 mode, but one is an A1 and the other is a B1, so it's not exactly the same. So there's a bit of a controversy. Anyway, you take the average of the 2, and you plot it into these equations and you get an output. There's a bit of a problem with this because of course the cis carbonyl is not as, the cis carbonyl here may be affected by the wingtip group on the nitrogen. And this is particularly evident in this cyclophane. So if you take these square planar rhodium and iridium complexes, the carbene heterocycle is orthogonal to the carbonyls, to the square plane. Almost perfectly orthogonal. So this carbonyl and this carbonyl, okay, they're all the same irrespective of, well, they're different, but if the groups are small, they're all the same. If the groups are a bit bigger, maybe they're still the same, but if the groups become 3-dimensional, the cis starts to get affected. So that's the case with adamantyl, and that has been totally extrapolated with this cyclophane. So now we put out of the cyclophane, with the cyclophane we put a layer up here. That's exactly where the carbonyl is. So your carbonyl starts to be repelled by the cyclophane, and of course this changes the stretch vibration. So now, do we change the donor property of the carbene because we see a different CO stretch? No, not at all. We manipulate the CO by other technologies. So the donor properties of this carbene should be exactly the same as this one. Electronically, these ligands are the same. But because of this cyclophane, we start to move away the CO, and as a matter, the CO stretch changes. So we have to be very careful when we look at these Tolman electronic parameters that we be aware that there could be steric factors that have electronic consequences. That's what we call stereoelectronic effects. So that may happen. And then Gusev has looked at this a bit more sophisticated. He had made a full table with, I don't know, 200 carbenes, where he looked at it, where he included as well the repulsiveness factor, which is basically the steric clash that you get in the 3rd dimension. And you can make a history out of this. I don't know what people really make with it. Maybe it just gives you a bit of a clue that bulky carbenes have a high repulsiveness factor, while less bulky carbenes have a lower repulsiveness factor. So there have been alternative modes. Some have looked at phosphines at the carbene-carbon of a spectator carbene. So you modulate this ligand L, and then you see how is this carbene here shifting. And that can tell you a bit how strongly donating, weakly accepting it is. Seems not to work too badly, but it's a hell of a job to get first the precursor and then to make the carbene. Others have used the cod wingtip group protons, the phosphine, but with the phosphine again you have paramagnetic factors in the NMR that you have to include in your calculations.